Okay, so this is lecture 22 on the proof complexity as a computational lens course. And we are going to talk today about size-space trade-offs for cutting planes. Let's just do a quick recap. So since we're doing size-space trade-offs, we're switching to this configuration style proofs again. So proofs operate with formulas. Now for cutting planes, it's going to be 0-1 linear inequalities. The proof is presented on a blackboard, and at every point in the derivation, you either download an axiom from your input formula, which will be a CNF for us. You infer something using the proof rules of the proof system in question, but only applied to lines that are currently on the board, or you erase things that you no longer need. And refutation, the refutation ends when you have derived explicit contradiction, which for cutting planes will be 0 greater or equal 1. And just to recap, so I mean, we are getting CNFs in, so to translate the clause to linear inequality, we just take a positive literal x is translated to x, and negative literal not z is translated to 1 minus z, and then we just collect all constant terms on the right-hand side. As we mentioned before, cutting planes makes perfect sense for any type of 0-1 integer linear inequalities, but we'll mostly do conjunctive normal formulas. So we know that all variables are bounded between 0 and 1. Those variable axioms we can always download, and then we can multiply by a positive integer. We can add to valid linear inequalities, and we can divide through by a constant and round up. So just to make absolutely sure we're on the same page, and also to quickly skip something that we talked about we never did, suppose we have the pigeonhole principle. And in this particular case, saying that 3 pigeons fit into 2 holes, then this is one of the formulas that we know that cutting planes can refute. So let's see just how we would do this configuration style. First, we have to translate this to linear inequalities. And then we could just start working on the hole axioms. So we say that for hole 1, not pigeons, it's not the case that pigeon 1 and 2 both go there. Pigeon 1 and pigeon 3 also don't go there. Let's sum this up. And let's sum that pigeon 2 and 3 also don't go there. So now we see that we can erase stuff we don't need and divide through and round up. And then we do the same thing for the second hole. And once we have derived that, basically at most 2 pigeons can use the holes. Then we just sum up all the pigeon axioms that say that every pigeon wants a hole. And erase. Pigeon 1 and pigeon 2, and pigeon 3 also wants a hole. And then finally, we can just see that on the whole side, we can take at most 2 pigeons, but there are 3 pigeons that won't hold. So we just add this up and we get 0 greater or equal 1. So again, this just shows, this generalizes that the pigeonhole principle in general, cutting planes, even if you give it the CNF encoding, you can recover a nicer cardinality constraints encoding, and then just sum up the number of pigeons, sum up the number of holes, and see that there are more pigeons than holes. And this is the way you could do it in line space at most 4. So the measures we care about is the total number of lines or inequalities in the refutation. That's the length. We care about size. We also count the bit size of coefficients. For space, as before, we can measure total space, which will be here the total number of literals plus coefficients. So really summing the bit sizes of all the coefficients. We'll also care about line space, which is the analog of clause space and monomial space. Again, the number of objects that the size measure measures. But we just look how many of those we need in memory simultaneously. So what have we seen about the cutting planes proof system so far? We've seen that the clique coloring formula, claiming that there exists a graph with an M clique and also an M-1 coloring, that is requires exponential size to refute. It's a quite involved proof, goes via interpolation and monotone circuit complexity. We skipped the monotone circuit lower bounds. And in particular, it's somehow clear that in order to do interpolation, we needed the formula to split into subformulas in a very specific way, which does not seem generally applicable. Yesterday, we saw lower bounds for random log n CNF formulas, which interestingly, the proof technique is somehow in the end reminiscent of the bottleneck counting argument for resolution lower bounds for the pigeonhole principle and for Thapen that we did in the very first lectures. And so I think it's fair to say that this is a quite intriguing and exciting paper. But also I think we do not fully understand how far you can push this. And again, there seem to be, you have this problem that you somehow need to be able to partition the variables in a nice way. And this is not always obvious how to do. So this is what we know about size. What about space? Well, there have been studies of versions of pebbling formulas, so-called lifted pebbling formulas. We'll talk in a bit what that means. And it has been shown, so for resolution, remember that we basically were able to prove that for pebbling formulas with appropriate variable substitution, we got closed space lower bounds in terms of the pebbling price. Here we can get such results, but only for certain types of directed acyclic graphs and only if the refutations are short. Okay, so we have space lower bounds for short refutations of formulas where we know that such short refutations exist and where there's no obvious reason to believe that there should be any trade-offs. Like looking at these pebbling formulas, they don't seem to exhibit trade-offs. So I like to, or have liked at least, to think of this as really space lower bounds in disguise, except we're not quite able to prove them unconditionally, only for short proofs. Similarly, this has also been proven for Thapen formulas with lifting. And here it's actually not so clear whether there even are short refutations of these lifted Thapen formulas. This is an interesting question because it's the lifting gadget is a small gadget. So we're not able to prove lower bounds, but it seems that these formulas might be hard. So this suggests that maybe we can view both of these results as, if we only worked hard enough, then we would be able to prove unconditional line space lower bounds that would maybe somehow match what we have for resolution, except for a polynomial. This is what you could hope. And what I tried to prove for a long time, except that then Galesi, Pudlák, and Thapen proved that in fact, cutting planes only needs constant line space 5 to refute any CNF formula or indeed any unsatisfiable system of 0-1 linear equations. This is a proof that we won't do. It's not too hard. It's a very nice paper. The coefficients will be exponentially large. So this means that we already have our size-space trade-offs, which is the topics of today's lecture. So we could maybe make it into a very short lecture. Because, well, we already have these conditional space lower bounds for short refutations, and now we see that indeed there are small space refutations. So this, if we just combine this Galesi, Pudlák, Thapen with the results I had on the previous slide, then we now have size-space trade-offs.
The coefficient being exponentially large means in value, or like exponentially many bits to write the coefficient?
Exponentially large in magnitude, so polynomial in magnitude. So basically, what you need to do, the proof will basically, it's a very neat proof. You will build linear inequalities that rule out more and more of the search space. So you start with the all zero assignment, and since it's an unsatisfiable formula, so there is some clause that says that this is not okay. So from this clause, you can derive that the sum of all variables is at least 1. And now you will carry with you that the sum of all variables is at least some number. And then in the next step, you say, what about one number larger? You plug in exactly that assignment. Like you viewed your variables now as expressing just an n-bit number. for the next assignment, you have some clause that says that is not happy with this. And now we just need to take the linear inequality that ruled out all smaller numbers and take this clause and somehow massage them together and get a new linear inequality that rules out this new number also. So you just start by 1 and count all the way up to 2 to the n. So, but this means that the linear inequalities will sort of wiggle through the Boolean hypercube in very interesting. Okay. So we even get, so size-space trade-offs for constant space, except that somehow the coefficients of exponential magnitude, yes, the line space is constant, but something seems slightly off. This is not the kind of trade-offs we want, I think. So you could ask for, in some sense, in quotes, true trade-offs. Can we find trade-offs where the space-efficient cut-in place trade-offs are really space-efficient? So where the coefficients are of polynomial magnitude at most, or say even constant magnitude. Okay, so this is what we want to talk about. And the focus of this lecture and the next lecture is indeed we can find such trade-offs, 6 CNF formulas that can be refuted with constant size coefficients in linear size but fairly large total space. So like I've fixed some concrete parameters here. So n to the 2/5, so something like square root n almost space. You can also get the space down to be very small, like n to the 1/40, but then the size is exponential. This is a true trade-off, okay? In the sense that if you go below n to the 1/20 in line space, then in fact the length, not only the size, but the length will be exponential. And as stated, so note that the upper bounds that we get are in terms of size and total space, so they're also counting the number of bits, and the lower bounds are just counting the number of lines. So in that sense, it's somewhat similar to in this sense to the trade-offs we had for resolution also had this, that the upper bounds were in terms of total space and the lower bounds were in terms of floor space. The way I stated it here, I'm only talking about cutting planes, and we will only talk about cutting planes. But in fact, the same formulas, you can plug them in and you get trade-offs simultaneously with these parameters for resolution, for polynomial calculus, and for cutting planes. So it's like one family of formulas that exhibit these trade-offs for all of these proof systems that we have been obsessing about in this course. I will not emphasize this, but this in particular means that the upper bounds that we probably will not have time to do are for resolution. And then once we get the lower bounds for cutting planes, that obviously translates also to resolution, and it's actually easier to get them for polynomial calculations. But that requires a bit more of an argument that we might or might not do. And I should also emphasize that again, depending on whether you view this as a strength or a weakness, but we actually have a stronger semantic model where at any point in time you can look at all of your constraints on the blackboard. And I don't care about the syntactic derivation rules. You can just write down any zero linear inequality that is implied in a single step. So this in particular means that these trade-offs hold in a model where any formula is refutable in linear length and a linear space, just by downloading all the axioms, staring at the formula, and saying contradiction. So even for this proof system, we have this trade-off. On the other hand, this is a weakness in the sense that if we're looking for supercritical trade-offs, then we know that we're not going to get it with these techniques, precisely because it's not able to distinguish what's going on in the syntactic derivation steps. All we know about the derivations are that, well, you derived something that is implied. Both a strength and a weakness. So this proof is at least the first half of the lecture today. I'll just tell you how the proof goes. It turns out that we really have to, well, the way we would phrase it in a paper is that we have a delicate chain of intricate reductions. You could also call it the kitchen sink if you like. We're basically throwing everything we have at it and see what sticks. Okay. So let me try to, now we'll spend a while to try to say how this is going to go. So first let's assume that we have a short space efficient proof. Then we're going to talk about the falsified clause search problem, which we heard about yesterday, I think. This is given the formula is fixed ahead of time, and then you're just given an assignment, and you should find a clause that is violated. There might be several answers. You have to just output one. And we'll somehow make this into a two-party communication problem, and we'll talk about a little bit about two-party communication because we haven't talked about this before. But somehow we will see then that if you have a short space efficient proof, this will give a very good protocol for this problem. Where the model that we will study is so-called real communication, and we will also care about the number of rounds, and we'll get to this in a bit. Okay, so next step is that good. So then we have supposedly a efficient communication protocol for the search problem. Now it turns out that this search problem, if you construct your CNF formula in the right way, you can view it as a lifted or composed search problem. And then we leverage some of the exciting progress made in communication complexity over the last decade to show that from such a protocol, you can actually extract a decision tree for a much simpler problem. Okay, so now we're looking at, now we have a problem, and this getting ahead of ourselves a little bit, but this will now be a pebbling problem, and we're actually having a decision tree that will be solving the falsified clause search problem for just a vanilla pebbling formula with one variable per node. Okay, and here we're diverging a little bit because now we know, okay, before for resolution, we will now start to look at black-white pebbling, but instead we're going to look at the Dymond and Tompa pebbling game and say, oh, but a parallel decision tree gives me a very good pebbling strategy for one of the players in this game. And then we construct graphs for which these strategies are impossibly good. And now if we just concatenate all of this, this means that there couldn't have been any short space efficient. Okay, so so where does this come from, the different techniques? The fact that short space efficient proofs can give efficient communication protocols is a simple observation. I think it was written down first, maybe in Lund and Nordström, but it's sort of in some sense in the air, maybe. There we crucially did not realize that we should use real communication. So this is a later, and also the round efficiency was not a concern in that paper. Then parallel decision tree goes all the way back to Valiant, and the simulation theorems, as I mentioned, this is an old paper by Raz and McKenzie, which was revived and much improved by Göös, Watson in 2015, and has led to lots and lots of exciting results in communication complexity, in circuit complexity, improved complexity also in other areas. And really even if you don't care about cutting plane size space trade-offs per se, the real reason to still care about this lecture is that what we'll mainly be occupied with is to understand this communication complexity problem and the simulation theorem. And this has turned out to be a very powerful tool being behind some of the very latest, very most exciting results in proof complexity. So we'll look at this today and next lecture, and then we'll revisit different flavors of this communication simulation framework also in coming lectures, most of the lectures that remain. Pebbling formulas we've already talked about, of course, so that's kind of stands to reason that they will make our favorite formulas will make a reappearance. The Dymond Tompa game has been studied long ago. It was maybe a little bit unexpected that it would be useful here, but it is. And then finally, the graphs, it turns out that we can use ideas from the previous papers that use black-white pebbling game. But since the Dymond Tompa game is different, we're going to need to hack together slightly different graphs. I'll say a little bit about this, but probably not too much. Okay, so this is like the overview. Now we'll try to flesh out a little bit more about these details, and then by the time we get to working on the whiteboard, we're going to focus on communication complexity. Okay, but since I think many of you know what communication complexity is already, but just to make sure we're all on the same page, let's start with the basics. which is standard deterministic communication. So we have Alice and Bob, following a Q tradition. They're both deterministic. They have infinite computational powers. They can solve even undecidable problems. The problem is that the input x and y is split between them, and they need to compute a function that depends on both x and y. So since they have, computation is not an issue at all, the resource we're bounding is communication. How many bits do they need to exchange? So they can devise, they know the problem in advance, they know f in advance, they don't know their inputs, so they can design a protocol, which is a binary tree, which in every node of this tree, it says whether Alice is going to speak or Bob is going to speak. And what Alice says, if it's Alice's turn, is only a function of the node where we are in the tree and Alice's bits, nothing else. And Bob can only speak based on the node in the protocol tree, which sort of says what we've learned so far, plus his input. And then we count what is rounds here. Well, it could be that in the protocol tree, Alice speaks, and then we, depending on whether she says 1 or 0, in the tree, we have two edges labeled 0 and 1, and then we move along the appropriate edge. Then if in the next node, maybe Alice should speak again, so she'll speak for a while, and maybe in the next node also, but finally we switch to Bob, and that starts a new round. So we count the number of alternations between Alice and Bob. That's the number of rounds. The other thing we count is the total number of bits set. Does this make sense? And when we, let's insist also that when we reach a leaf, in that leaf, Alice and Bob automatically know what the value f is. Okay, if f is a Boolean function, this is maybe not so important because one extra bit would just, whoever knows can tell the other party, but we'll actually also have non-Boolean outputs. So let's insist that Alice and Bob both know when we reach. We say that a function is solved by an R-round deterministic communication protocol in cost C. The total number of bits sent by Alice and Bob in a worst case scenario, so along any path in the protocol tree, is at most C, and there are at most R alternations between Alice and Bob. But we're going to, the results need a stronger model, which is real communication. So still Alice and Bob, still with their private inputs, X for Alice, Y for Bob. And they should still compute some specified function f, but now they compute by sending real numbers in infinite precision to a referee. And in each round, depending on which node in the protocol tree we're at, Alice sends C sub v, real numbers, and Bob sends C sub v, real numbers. Again, in infinite precision, we don't pay for this. The referee collects this number, makes a pointwise comparison, and then announces a bit vector of length C sub v, telling whether Alice's coordinate is less equal to Bob's coordinate. And those bits are the things that we pay for only. And again, we say that the function is solved by an R-round protocol in cost C in real communication now. If the number of rounds where both Alice and Bob now speak in each round is R, and the total number of comparisons made by the referee for along any path in the protocol tree is C. Now, it's not so hard to see that, firstly, this is a stronger model than standard communication. You can think about it like if Alice and Bob wants to simulate a standard protocol, they can do it with a real valued protocol. Think about it. Also, if you know about deterministic communication, the classic hard problem is the equality function. Alice gets an n-bit vector, and Bob gets an n-bit vector, and we're just interested in if it's exactly the same bit string. We know that this requires a linear amount of communication for the deterministic communication. If you think about it in real communication, you'll figure out that we only need one round, we only need 2 bits. And you can think about this. If you can figure it out. Okay, so that's real communication. Are we happy with this?
Then here, cultural videos and the games, cultural videos, and they are trivial for real communication then? You just send your all input bit? Your all input string? Both of them send them to the referee and then...
But that's high communication, right?
Yeah, okay.
So again, we're going to
yes.
yeah.
Yes,
So if I'm only what if I only care about optimizing round efficiency? Then send all your input.
Yeah.
But this is a sort of a multi-objective problem, right? I somehow want a few rounds, but also little communication.
Yes. Sir.
Yeah, but this is a good point. So I should say this, that note that if I only care about, so what should I do if I want to optimize the number of rounds? Then in one round, Alice just sends her bits basically, and Bob can solve, right? That's true also for deterministic communication. Right. What do I do if I only want to minimize communication? Well, then you sort of see that you're giving up power if you have to commit to sending several bits in advance. But it would be more efficient to only send one bit at a time and then take it from there and see what Bob answers for Alice, for instance. So if you want to minimize cost only, then you only set one bit at a time and then realize that maybe you can save. So the whole interesting thing is there's a tension between optimizing the number of rounds and the total communication, and this is what we need to use. Make sense?
Yeah.
Okay. Thanks for the question. Very good. Okay. So falsified clause search problem again is the problem where we have a fixed CNF formula F, which is unsatisfiable. We get an assignment alpha. Since the formula is unsatisfiable, there is at least one falsified clause, maybe many. I'll put just one. I'll put the index of a falsified clause. And we have seen, so where does this come in? Well, we've seen, so I'm repeating some stuff that we already know, but we've seen that any standard proof system gives you a way of solving this problem. How? Well, you start at view the proof as a DAG. You start at the sink of the DAG, which is contradiction, which is violated by every constraint, every assignment. And then given alpha, you just walk back through the proof tag and you walk along falsified nodes. And you know that since every successor node follow from the premise nodes and the proof system is sound, if the conclusion is false, then at least one of the premises is false. Maybe both, but at least one. So I pick one way of walking through the DAG backwards until I hit a source, which is an axiom clause, which is falsified. This is a valid answer. So this is the connection why, if you have a refutation, this gives you a way of solving the falsified clause search problem. And implicitly or explicitly, many of the lower bounds we have done are playing with this, that if a proof in some proof system is too short to be true, then we will get a too efficient way of solving the falsified clause search problem. And this is what we're going to do today also. Except we need to somehow make this into a communication problem. So there's not only formula F, there is some kind of partition of the variables between Alice and Bob. And now Alice gets an assignment to her variables only, Bob gets an assignment to his variables only, and now they need to communicate to figure out together what a falsified clause might be. Note that I'm slightly deviating from how I defined communication before. This is not a function. Right? In general, there might be several valid outputs, and this actually makes our life harder. So it's harder to prove lower bounds for relations than for functions, but it's not important for us today. So we can ignore this distinction. But it is in general important that the falsified clause search problem is a search problem. It's a relation. It's not a function. Okay, good. So now I claim that if I have a succinct refutation in a proof system, by succinct I mean it's reasonably short, it's also space efficient, that gives me a communication efficient and round efficient protocol for solving the falsified clause search problem. Okay? And I think we can almost do this proof by picture, it's not hard. So we'll just do binary search. So you're given alpha. Alice and Bob both know without even evaluating that the very first configuration is empty. So it is satisfied by the assignment alpha. The very last one is contradiction. It's violated by alpha. So we just do binary search to find a transition. We look in the middle, and Alice and Bob somehow together evaluate for cutting planes, they would evaluate together the linear inequalities. How would they do this? Well, basically, they know what the constant term is. I mean, Alice could shift her her part of the linear form to the right-hand side, and then we basically want to know whether the constant term minus Alice's bits is less equal Bob's bits. Okay, so this is what they could send to the referee. And doing this, they can evaluate, and it turns out that the middle configuration in the configuration style proof is false. Well, then they both know this, so they do binary search in the first half of the proof and find out that it's true, true, false, and finally they find there has to be one transition point. Potentially many, but at least one. Okay. Let's think about how can we transition from a true to from a satisfied to a falsified configuration. It can't be an erasure, obviously. It also cannot be an inference step because the proof system is sound. So what happened at this point is an axiom was downloaded. But that axiom is then the answer to the falsified closed search problem. So it's like a very simple observation, but powerful. Okay. And now the neat thing is let's think about what is the communication complexity of this. So we need to evaluate, binary search will need log length of proof number of blackboards that we need to evaluate. Okay? And if you think about evaluating the formulas in a configuration, Alice and Bob both know. So this we're going to be able to do in parallel. Just know that we have these maybe S inequalities, these we can evaluate in parallel. So the number of rounds is going to be log n. How can we evaluate the configuration? Well, if I know that the number of inequalities is at most S, then clearly Alice and Bob needs to send only S real numbers to the referee. Okay? So that means that the total number of communications, so log L rounds and S times log L bits in total. Okay? So this means that, again, if I have a proof, a refutation of the formula in length L and space S, then I get a protocol for the falsified closed search problem with total communication S log L and log L rounds, which in general will be, I mean, if we think of the proof as being polynomial length, then log L is logarithmic. So it's going to be very round. Okay? And the way you can do this for any proof system, as long as you tweak appropriately the model. If you think about it for resolution and for polynomial calculus, it's actually sufficient to just have the deterministic model, because for Alice and Bob, if we have clauses, then Alice just needs to evaluate her part of the clause and Bob his part of the clause, and that's just 2 bits. For polynomial calculus, they just need to evaluate monomials, and for every monomial, Bob does his part, Alice does her part, again 2 bits. Okay, so this means that, and this is why if I can get lower bounds in the real communication model for cutting planes, then for free I also get corresponding lower bounds for resolution of polynomial calculus. Does this make sense? Okay, so now we come to the composition or the lifting. So we need to somehow, the point is now that we want to construct a search problem in the form of a falsified closed search problem that is too hard for such a protocol to exist. Okay. How do we do this? Well, we use composition or lifting. So what's the idea? We start with a function f. Here it is a function of 3 bits. And then to turn this into a communication problem, we have a parameter L that is the lift length. And just to fit on this slide, the lift length is pretty small. It's just 2. Okay, in general, you should think of the lift length as being, we'll see, it's going to be a large polynomial. Here it is just 2. And what we do is we give Bob, for every variable in the original problem, so f is now a ternary function, so Bob will get 3 bit strings of length L. Alice will get 3 indices between 1 and L. And Alice Alice's indices identify which bits are relevant for Bob. And the composed function is defined as letting Alice pick from each bit vector a bit from Bob that should be plugged into the function. Okay? And the composed function is just in every coordinate, we look at Bob's bit string, let Alice index a bit, feed that into original function f, and a value. That's the lifted function. That's the lift of length L of f. And now you see that this gives rise, I already started talking about Alice and Bob. It's very clear that we will have a natural partition between the x variables that are selecting and the y variables that are the bit variables. Does this make sense? So, okay, good. This is like an extremely important notion. Okay. And now the point is that my claim is now for a problem like this, this is where basically we're going to say, okay, suppose that Alice and Bob have a good protocol for computing a lifted function like this. I'm going to connect the complexity of such a communication protocol to a decision tree for evaluating the original function. So what's a parallel decision tree? A parallel decision tree is a decision tree that cares about rounds. So in a normal decision tree, you just ask about one variable at a time, but now we want to minimize the depth, which is the number of rounds. So to minimize the depth, you can ask about several variables at the same time. Okay? Why is this good? Well, because the depth decreases. Why is it bad? Well, because here, for instance, if you would ask about y first, then maybe you would have realized that for certain values of y, you didn't need to ask about z. But now you have to ask about them at the same time. Okay? So every node is labeled by variables, by say, a set of variables v sub t for every node t. And then you have 2 to the v sub t outgoing edges, because you need to look at all possible outcomes. And then as before, the leaves will be labeled by answers. Okay, is it clear what a parallel decision tree is? So and what do we care about? We will care about the total number of queries made. So again, the parallel decision tree will query variable values in the input, and it will try to query as few positions as possible in order to be able to fix the value of f. Okay, so one thing we care about is how many bits did you query? That's the query complexity. But then also we care about the number of rounds, which is the depth. And again, clearly we have the same situation. What if I want to minimize the depth? Then in just depth 1, let the root ask about all variables, and you have fan out 2 to the end, and then you have the answer. But then the query complexity is terrible. What would a standard decision tree do? It would only query one variable at a time, but then the depth might be fairly large. And now the question is, what if we want to have both small query complexity and small depth? Can we prove lower bounds for this? Note now that if, and we say that, yeah, a decision tree solves a search problem if given alpha, we end at a path labeled by some q such that alpha q is in the relation, is in the search problem. So again, for the falsified clause search problem, which is what we think about today, a parallel decision tree solves the falsified clause search problem if, when you reach a leaf, you have identified the index of a falsified clause. Clearly, suppose you have an amazing parallel decision tree. And suppose Alice and Bob want to run a protocol. Then it's not hard to see that a decision tree come in handy, right? How would they use the decision tree? Well, at every node, if the node says that you should query a certain coordinate, then Alice will just tell Bob, oh, for this coordinate, my index xi is this position. And then Bob will say, oh, in my large bit vector, that position is actually this bit. So Alice and Bob can just simulate this decision tree to solve a lifted search problem. Is this clear? Okay. Okay. So this is the easy direction, that if I have a good decision tree, then I get an efficient communication protocol. Now, the miraculous direction is this is actually the best you can do. And this is somehow the technical heart, and this is what we're going to talk about. So for any search problem with a Boolean domain, so 0, 1 to the m, suppose that the lift is long enough. In the paper we're going to cover, we have m cubed plus a bit. You can push it down a little bit. And I'm actually not on top of exactly what state of the art is. We would really like to, I think you can push it down to linear maybe, but I'm a little bit hazy on this. It would be super exciting to push it down to constant. This is a big open problem. We're going to get m cubed, essentially, plus some slack. Okay. So if I have a search problem, and if I lift it with a lift length that is m cubed, where m is the original number of variables, and if Alice and Bob have an efficient real communication protocol in R rounds, and total communication cost C, then in fact, as it were, I can say, well, the only way they're doing this is they are in fact simulating some parallel decision tree, which has depth R and has cost essentially C. In fact, C over log n, so I say. Okay, so the way this proof will go is that given any communication protocol, I will extract a parallel decision tree. And this is a simulation theorem in the same way as, if you remember, when we had resolution refutations of pebbling formulas, we extracted black-white pebblings. So like even if the resolution prover claimed not to know about black-white pebbling, we sort of extracted the implicit pebbling. So here, Alice and Bob maybe claim that they've just come up with a very clever protocol. They didn't think about parallel decision trees at all. We'll just say, well, you kind of did, because here's a parallel decision tree that you use. Okay, so finally, where do we get the formulas that will give us trade-offs? Well, we'll turn to pebbling again. So here are our favorite pebbling formulas, which are defined over directed acyclic graph. Again, we're using the pyramid of height 2 as an example. So we have axiom clauses saying for all the sources, we have unit clauses saying that they are true. So U1, U2, and U3 are true if I identify the variable and the vertex here for simplicity. And then you have so-called pebbling axioms saying that the truth propagates upwards. So if U1 and U2 are true, then U4 are true. If U1 and U3 are true, then U5 is true, and U4 and U5 true forces U6, the sink, to be true, but the sink has to be false. So this is the pebbling formula, which, as we've seen, has appeared in many contexts, in particular, has been used for resolution closed-space lower bounds and trade-offs between length and closed-space, and also for polynomial calculus. We've also seen in this setting that we cannot use these vanilla pebbling formulas because they're trivial, so we somehow have to modify them to make them harder. What did we do before? Well, we substituted every variable by a function, by a gadget like XOR or majority or something like this. Now we'll do lifting. Okay, and the idea is we somehow want a formula that morally captures, encodes what a lifted problem is that we had before. Okay, again, so let's see. So basically, we want to do this thing, but for a CNF formula. Okay. So how do we do this? So we basically, Alice should have an index, and we're going to encode that index just with indicator variables. So X is an integer between 1 and L. I just have L Boolean variables, and the intention is that I'll set one of them to true, and that is if Xij is true, then the ith coordinate of Alice is J. And Bob's coordinates are going to be, as before, just a bit string. Okay, so I'll refer to Alice's variables as the selector variables, which is the indicator encoding of her indices, and Bob just has, again, a bit vector of length L for every variable. And now we have, for every original variable, we have an auxiliary clause saying that Alice needs to pick, she needs to have some value for this coordinate. And then for every original clause in the formula, so suppose that the C UI1 or all the way up to UIS, or not UIS plus 1, or all the way up to not UIT, for any such clause, and for any tuple of length t of possible coordinate values for Alice, there is a what we call a main clause, which is a bit of a beast. It basically says, so what this clause says is that you have all the selector variables xi1, j1, xj2, j2, xis, js, and if Alice has not selected exactly all of these coordinates, then one of them is false and the whole clause is satisfied and we don't worry, right? However, for the j tuple that corresponds to exactly Alice's selection, we get back the original clause. So we're sort of packing an exponential number of copies of the original formula in an efficient way. Yes?
Is that important here that your selector variables are kind of like choosing in unary instead of binary?
No.
No, it's not? Okay. Then you would just have the auxiliary clause, but I guess...
There have been different variants for this. I think you can do yeah, I don't think... I mean, we will definitely use it today, but I mean, you can... Yeah, I think you can play with it.
Yeah, I mean, would the lower bound still hold if we replace
the exact one we're doing now? I'm not sure.
Okay.
I'm not sure.
So
maybe. Yeah, I actually don't know.
You don't need an auxiliary direct, but you do the main clause would be rewritten. Yeah, right. You don't need
so that is. I'm not sure.
Yeah,
I'm actually not. I sort of. I mean, we're not. It's a good question. I don't know. We should have to work it out. Okay. Just to see, here is again the Pudlák formula from before. So now I want to do a lift of it, but again we have to do I'll do a lift of length 2 again, just because it gets bad enough. So here's the lifted Pudlák formula. So you just see here are for the source axioms, you say that node 1, you have like either if okay, it seems that some negations here are off. Okay, I need to think. These should be negated, I think. This seems to be wrong. Something weird has happened here. I think these should be negated, and here you should have y's. No. Sorry. Okay. These are the auxiliary clauses. Sorry, you're saying so for node 1, pick index 1 or index 2. For node 2, pick index 1 or index 2. For node 6, pick index 1 or index 2. Sorry. Okay. And then once you have this, you say, okay, fine. For the sources 1, 2, 3, if the first index is picked, then y11 has to be true. If the second index is picked for node 1, then y12 has to be true. And similarly for the others. And then for the Pudlák axioms, we will now get, I guess, 8 clauses, if I'm counting correctly, where you just say for every possible tuple that picks between 1 and 2 for the first predecessor and between 1 and 2 for the other predecessor, and you pick between 1 and 2 for the successor. For all of these combinations, if this is the tuple you pick, then the Pudlák axiom has to hold. And finally, we get for the sync that if you pick sync index 1, then y61 is false. If you pick sync index 2, then y62 is false. Is this kind of clear? Sorry for messing this up. And again, like in general, this will like be a massive formula, but the point is that if we start with a KCNF formula, although we're sort of packing in an exponential number of formulas, as it were, we're actually doing it without an exponential blow-up. We only take a blow-up in K, which is the maximum width of the formula. This is very important. Okay, and now if we plug in the simulation theorem and suppose that we have an all-round real communication protocol for the lifted Pudlák formula that we saw on the previous slide, then that will give us a depth R parallel decision tree that solves the search problem for the original Pudlák formula. Okay, so we need to, so the final thing we need to do is to study decision trees for Pudlák formulas, which we can do in terms of Pudlák games, except not the black and black-white pebbling games that we loved before, we're going to study Dymond and Tompa, which interestingly has a relation to reversible pebbling, but we won't talk about that today. So Dymond and Tompa pebbling, this game is kind of reversible pebbling in disguise, but that's the fact that this is so is in fact like this is a paper. And Dymond and Tompa is the nice way to think about reversible pebbling if you want something that measures rounds. Okay. So here's the game. We start with a DAG, and again, we have a pyramid as an example, but it could be any DAG. There are two players, the pebbler and the challenger. In every round, the pebbler will place pebbles on a bunch of vertices. In the first round, pebbler has to pebble the sink. In all other rounds, the pebbler can do whatever. Okay? In every round, the challenger either stays at the vertex where he currently is, but he is nowhere in the first round, so he has to go somewhere. And the going somewhere or jumping somewhere is you can jump to a newly pebbled vertex, a vertex that would pebble in this round. Okay? If you jump, then great. But then if you didn't jump, then all the pebbles go bad and you can't use them again. Okay? And the pebbler wins, finally, when the challenger is on a vertex where all immediate predecessors have pebbles on them. Okay, so let's play this game. So pebbler maybe starts by playing these two, and challenger has to jump now, has to take a position in the graph. It's probably a good idea to take the sink. Okay? Now this means that this pebble is now inactive. It's never going to be used again, the green one. Now pebbler pebbles these blue vertices with pebbles. And the challenger says, thank you so much, I'm good where I am. Now these pebbles go inactive. Pebbler again pebbles these two vertices, same. And now challenger, for some reason, decides to jump. And now all pebbles go inactive. And now it's kind of clear that the challenger is in bad shape. Pebbler just places this pebble, and now challenger, I mean, if challenger stays or moves, doesn't matter, challenger has lost, right? Okay, so what are the resources we care about? We care about the number of rounds, and we care about the total number of pebbles placed by the pebbler. So now the theorem is that if there is a depth R parallel decision tree with at most C queries, then pebbler can win the R round Dymond Tompa game, with at most C plus 1 pebbles. This is in fact almost not a lemma. This is like the correspondence is extremely tight. Okay, is the statement clear? Okay. So now we actually have everything in place. So this is like now we have seen everything in the proof. Now we just put things together. Again, I'm telling you what we said before. Oh, yeah. So first, what do we do now? We somehow figure out good graphs that have strong trade-offs between number of rounds and total number of pebbles placed. So this is something that we need to prove. So it turns out that our black-white pebbling lower bounds are somewhat helpful. Sort of, we can get ideas for good graphs, but we have to hack them a bit because the Dymond Tompa game is different. Okay, so suppose now we start with a graph G that has a strong trade-off in the Dymond Tompa game. By what we just had on the previous slide, that means that there's a strong trade-off between depth and query complexity for parallel decision trees. Yes, for the search problem for the pebbling formula over this graph. Now we lift the pebbling formula with a suitably long lift. This means that the parallel decision tree depth query trade-off lifts to a real communication trade-off between number of rounds and communication. Okay. But this means that we can now lift this to actually, so there's a twist here now. So we're actually looking at the lifted search problem for the pebbling formula. And now it turns out that if you just think about it, we can actually sort of lift and search commutes here. So now we look at the search problem for the lifted Pebling problem. We have to make an argument for this, but it's not so hard. Maybe we'll get to it in a minute. So it turns out that basically, if I have a good communication protocol for the search problem for the lifted Pebling formula, then exactly that same protocol will work for the lifted search problems. Because basically that you can run the same protocol except that no auxiliary clauses will ever be violated. Okay. So, but that means now that if we had a real communication round cost trade-off for the lifted search problem, we have the same real communication round cost trade-off for the search problem for the lifted CNF formula. Okay, but then from what we did at the very beginning, this means that there cannot be a short space-efficient proof for this lifted Pebling formula. So we have a cutting picture between size and space. Okay. So it's time to take a break and then switch to the board. Just to say and now we're going to do some more details, but again, as I already said, the main technical meat and the main thing that we're interested in is to understand the communication complexity and the simulation theorem. How can you relate decision trees to communication protocols? This is where the technical meat is. I mean, there are technical meat in different parts of the paper. Also, the Dymond and Tompa lower bounds are non-trivial. But this is somehow the really fun part and the part that the simulation of to extract the decision tree from a communication protocol. This is what will come in handy also in future lectures, and what has turned out to be so useful. But what are possible open questions that are interesting? So as I already said, the lift length is fairly long. It's like cubic in the number of variables. It would be great to get it down to sublinear or even constant. One thing that we will see coming up in future lectures is to take the simulation theorem we have today and lift it to stronger communication models. What do I mean by this? Well, one thing you can do is, we'll talk about it, there is a version of sort of communication complexity within quotes where you don't have protocol trees, but in some sense you have protocol DAGs, directed acyclic graphs. And it's very interesting if you can extend these lifting techniques to protocol DAGs, because in some sense, protocol trees correspond to tree-like proofs. Protocol DAGs actually correspond to fully general DAG-like proofs. So this is one direction, and indeed, hopefully in like a week or two, Kilian will tell us how we take what we will do today and next lecture and actually extend it from protocol trees to protocol DAGs. Another direction, which some of you will be well aware of, is, well, there are other communication models that capture, for instance, resolution with parities, where we would also be very interested in having similar type of simulation results, but where we don't have them. But this would give like stronger proof complexity lower bounds. And indeed, many of the exciting lower bounds, recent lower bounds for res parity has a communication complexity flavor. For the proof complexity, so we won't talk about Dymond and Tompa, but definitely stronger trade-offs for Dymond and Tompa would be fun. The fact that we need to reduce to this Dymond and Tompa game is a bit funky. It seems like if we could reduce to black-white Pebling, then we might get stronger trade-offs. Morally, I believe it should be possible. I have no idea how to do it. I tried, I failed. We talked about that this semantic model is a little bit too strong for comfort. For instance, if we take these Thapen formulas on long skinny grids, is it conceivable that we have supercritical trade-offs? We don't know. The techniques we're going through over now cannot possibly establish such lower bound. We have no idea how to do this. We know that apparently if you have unbounded coefficient size, then line space is constant. But what if I tell you that the magnitude of the coefficients should be at most polynomial? So at most logarithmic number of bits. Can we then prove space row amounts for cutting lengths. This is a somewhat big open problem. And again, we're going to talk more about communication, about simulation theorems in future lectures. It's going to show up. Different types of proof complexity results are going to be, we're going to reduce them to different types of communication complexity problems. Playing with, we saw deterministic communication, we saw real communication. You can also talk about so-called randomized communication, where Alice and Bobs have access to randomness and only need to produce the answer with high probability. And we'll talk about some of this in future lectures. But now it's time for a break. And then we're going to get whiteboards set up, and then we're going to start doing proofs. Questions on what we did so far? Then let's see if we can figure out how to take a break. So we're now back after the break. We'll just have some key definitions written down, and then we'll do the communication complexity. Okay, so I just wanted, so what's a search problem, just to make sure? So a relation or a search problem S lives in Z Cartesian product Q, where we think of the input domain as being the input is Z, and the range or output range is Q, and basically the task is that we're given a Z, we want to find a Q such that ZQ is in the relation, and we assume that it is always possible. So we're going to assume that it's a total relation. So for any Z, there is a Q. In particular, we're going to mostly talk about falsified clause search problems, and it's clear that a falsified clause search problem, given a truth value assignment, there always is a falsified clause. But actually, the lifting, by the time we get to the lifting results, we could not care less that we're doing falsified clause search problems. But it's just, we just observe that it's total. Okay, and so just to be absolutely sure that we know what the lift of length L is. So I'm going to denote that lift sub L of S, except we're probably L is going to be the same always. It's going to be the input domain is going to be 0, 1 to the M for us, and the lift length L is always going to be M to the 3 plus some positive epsilon for a constant epsilon. So I'm probably going to start dropping L. So lift L, that's the search problem that lives. So the input domain will now be L.
Are you recording?
Yes.
Ah, okay, sorry. I didn't create.
Yes, thank you for checking. I think we are recording. Does it seem like we're recording?
I didn't check. I can check.
So
You checked.
Yes, it says recording.
okay. So the input is now M numbers between 1 and L times M bit strings of length L. The range is still Q, and we say that X, Y, Q is in the lifted search problem, I'm emphasizing that x and y are vectors. I'm probably going to run out of energy to write those vector arrows also very soon. So for x and y, input q is a valid output to the lifted search problem if, again, what we said, that what you do, you take y1 and pick in this bit vector, you take the coordinate specified by x1. For y2, you take the coordinate specified by x2. All the way up to ym, you take the coordinate specified by xm. This comma q should live in the original search problem S. Okay, and x will refer to them as selector variables, and sometimes we'll talk about the y's as main variables. Okay. Also, one piece of notation. This is known as the indexing gadget because basically x is indexing in y. So we will use the notation. We'll use the notation index xi yi. This is just the bit in the y string that is indexed by I, and this, of course, then this same notation extends to the bit strings in the obvious way, right? So this will be like, again, y1, x1, all the way up to ym, xm. So I should just say, okay, maybe one quick thing. When you do the lifted CNF formulas, you're gonna, the y variables, you don't need to do anything with them. The x variables, you're going to encode them as indicator variables. You could potentially encode them as binary strings, like a binary encoding, but we're not going to do that today. I just want to say that if f is a KCNF formula with m clauses, if you do the math, then lift L of f is going to be a like all the original clauses, they just blow up by factor 2 because we have a selector variable and a main variable. But then you realize that the lift length also comes into the picture because of the auxiliary clauses. So we will get a max of ln 2k in that formula. And the number of clauses will be at most, well, we'll have, if there are n variables, we'll have n auxiliary clauses, and then we have m times L to the k. And the important thing is again, that we only, the blow up of the formula, we're only picking up a k here and not an n, and this is like important. Now, if you noticed, we actually stated the results that we're going to get for 6 CNF formulas, whereas the lift length here is polynomial, so that doesn't quite add up. So we're just, one thing that I'm going to sweep under the rug is, well, the wide clauses of the auxiliary clauses, just turn them into 3 CNF in the standard way. It really doesn't change anything. And of course, it's an easy exercise that f is unsatisfiable if and only if the lift is unsatisfiable. And then I said that actually our protocol will be for this search problem. So I just want to point out this is sort of a technical thing. I promised we'll move to communication complexity, but this is about communication complexity. The protocol that we get from the proof, the protocol that we get from the CP refutation is for the search problem, for the lifted formula, the communication problem that we want to solve is actually the lifted search problem. Right? If we look at the cutting place refutation is going to be for this formula, and it solves the search problem for the lifted CNF formula. The lower bound that we're going to prove is we're going to take the search problem for the original formula and then lift it. These are different things. But the point is that this is a harder problem than this one. So basically, if Alice and Bob have a good protocol for this, then they can use it to solve this. Because, okay, so Alice and Bob wants to solve the lifted search problem. So Alice gets her coordinates. She just translates them to binary. Like, you know, for every index x, she just sets one bit to true and all the other to false, and then they run this protocol. So since we're going to have an upper bound for this, this gives us an upper bound for this, meaning that a lower bound for this gives us a lower bound for this. Okay? And then we said that, yeah, so binary search, we talked about this, that's fine. The simulation theorem that we're going to prove, except that I'm going to cheat you a little bit. But let's write down the simulation theorem that I could have proven for you, except I won't quite, but suppose again that S has domain 0, 1. This is a search problem. Suppose that L is M to the 3 plus epsilon, or epsilon positive. So if there is a real protocol, real communication protocol, I really can write, with R rounds, and the total communication cost is C. If there is such a protocol that solves the lifted search problem, that solves lift of length L of search, the search problem S, then this implies that there is a parallel decision tree in depth R and big O of C over log L queries that solves the original search problem. Okay? This is the technical meat. This is what we're going to focus on. I want to say one more thing about the proof complexity. This will give us the lower bound, but in order for it to be a true trade-off within quotes, where this true means whatever positive quality we care about, we also need the matching upper bounds. I cheated you on those completely. So for standard pebbling, if you remember, when we did with XOR substitution, for instance, you could take, if you had a black pebbling, you could simulate it efficiently in the same like length corresponding to the pebbling time and space corresponding to the pebbling space. Okay, so that you can kind of do here as well. To get the short proof, you basically simulate a black pebbling, but you have to do it a little bit carefully now, because the point is that you can't just that a vertex is true. Note that you're going to get a huge space blow up for this. Just to say that the vertex V is true, that's going to be like L clauses, which is a large number. So the short refutation works fine, but you're going to have a pretty substantial space blow up. The space-efficient refutation, you have to do something different. The space-efficient refutation, we're basically going to use the Dymond and Tompa upper bounds, and we're going to turn that into a tree-like resolution refutation that is shallow, somewhat shallow. And then we just say, oh, a decision tree for a formula will give us a space-efficient tree-like resolution refutation. Okay. There are some details to be ironed out there. It is a little bit annoying, and you have to be a little bit careful. But it's not rocket science, and it can be done. I just want to point out that we do need these upper bounds. I'm just completely cheating you on this upper bound. Okay, good. So this then we can start talking about the interesting thing, which is the simulation theorem. And just to give the bad news right away, actually, we won't do real communication. Because there's so much, I mean, it's going to be complicated enough as it is. We're hopefully going to do it later in the course, but as a warm-up for this lecture and the next, we're actually going to do the proof for standard deterministic communication. And I think it's going to be like almost all of the ideas are there, and then there are some extra technical twists if you want to push it all the way to real communication. But for this and the next lecture, it's challenging enough to do it for standard communication. What this means is that we're actually going to prove not trade-offs for full cutting planes, but for cutting planes with polynomially bounded coefficients. Because if you think about it, for polynomially bounded coefficients, Alice and Bob can actually use standard communication to implement this binary search in the tree. Okay? So, but still, the general idea is to argue that if there is an efficient communication protocol for Alice and Bob for the lifted search problem, we can extract the decision tree for the original problem. Okay. So what is a decision tree? Well, a decision tree is a directed tree, right? With non-leaf vertices labeled by variables, edges are labeled by values, and then when you reach a leaf, they're labeled by answers. Yes? Somehow, this is a view that will be a little bit hard for us to have, so we can take another completely equivalent view of a decision tree. So if you think about it, I claim a decision tree is any algorithm that has an offline phase where it can collect any information that it thinks is useful. Like the latest news, the daily paper, some math background. If Alice and Bob, our friends, have an amazing protocol for the lifted search problem, we can certainly, take note of that in an offline phase. Then in an online phase, a decision tree is an algorithm that does the following. It hacks away, it does communication, and it's not time-bounded. We don't care about the time complexity. So we're doing immense amounts of communication, and then we query the input. And then we look at the answer, and then we, again, do immense amounts of communication, potentially using the offline information that we have, and then we issue a new query. And then after a bunch of queries, but we don't have any randomness or anything like that, and we're not able to commute with the outside world during the online phase, the only thing we can do in the online phase is just query the input. And then at the end, we just issue our verdict and say the answer is blah. And I claim that such an algorithm is just, that's also a decision tree, right? I'm just saying it's because conceptually somehow, I don't know, maybe this is just me, but you would expect to be able to extract a beautiful decision tree, and you could probably do it, but it won't be so clear. So instead, we will actually extract an algorithm that actually in an offline phase takes the communication protocol from Alice and Bob and then sort of starts simulating it and uses this to issue interesting queries to the input. And it should be clear that if this is a fully deterministic algorithm, then again, the number of the depth of this tree is just, well, how many times do I query, right? Because in order to minimize the depth, the algorithm might issue several queries in one go without computation in between, without getting answers in between. So again, the depth will be the same and the total number of queries is still the same. I'm sort of just complicating a very simple point, but so I'm not gonna show you the explicit graph, but we're going to have an algorithm that takes a communication protocol and then queries the input in a deterministic fashion. Okay, so how will we do this? So we're going to fix a communication protocol. So the general idea is that we have a communication protocol. Hi. For a node in this communication protocol, let me denote XV, the inputs of Alice that are consistent with V, right? We are at a certain point in the protocol tree. What are the inputs of all inputs of Alice that could have led to this? Because somewhere in the middle of the communication, we've already ruled out possibly a large part of Alice's input. Similarly for Bob, Y sub V are Bob's consistent inputs. So when we sort of in our heads simulate the communication protocol, we're going to keep track of this, except that we need to maintain nicer sets. So we're going to have an Alice set that lives in X to the V and a Bob set that lives in Y to the V, but has nicer structure. Now, the idea is that as we go through the protocol, we're going to be worried. So we're sort of going to simulate the protocol in our heads, and that is obviously going to, as we move further and further down in the protocol tree, we're going to restrict these sets. And we're interested in information leakage. And one first important information is that we should really worry only about Alice. We should not worry about Bob. Okay, why should we not worry about Bob? Well, because the decision tree is sort of a trivial upper bound if we have m variables. The decision tree could just query m variables and be done. Okay, but the way we have lifted every variable for Bob is to m to the cubed plus a bit more bits. And Bob has absolutely no clue how Alice is indexing in this gigantic vector. So sort of poor Bob cannot really, even if he wanted to, he cannot leak like helpful information to Alice. Like he could, even if he wanted to leak helpful information about the single coordinate, he could only leak like a vanishingly small fraction, 1 over, I guess, square, m square information about this coordinate, and then we're out of our total communication budget. So Bob is not the problem. Alice is the problem. Okay, because if Alice starts leaking information in the protocol about what her coordinates look like, for instance, Alice might do something crazy. If we simulate the protocol, maybe Alice has the secret code. I'll send you the number 42, and then you know that I have the all zero index string. And suddenly Bob knows everything. And then, of course, when we simulate the decision tree, we have to realize that, oops, this is a very dangerous message from Alice's point of view. We won't take that path. Okay, so technically, and we'll make this precise in a bit, but we're going to, as we simulate the communication protocol, obviously, at some point, we're actually going to have to issue queries, like decision tree queries to the original input. But we're going to keep at all times a non-queried index set, the non-queried coordinates, I. These are the coordinates in M that the decision tree that we're building has not yet queried. For those coordinates, we want to make sure that there are no weird correlations, so that suddenly, Alice sends a few strategic bits and Bob suddenly knows everything. So informally, what we want to say is that for every coordinate in I, we want it to be true that even if for Alice, we fix all coordinates in I minus this coordinate. So say that Alice would somehow just commit to all other positions what her coordinates have, what her coordinates are. There should still be many choices for what the value xi is. Okay, basically, like this would be an extremely, if we manage to maintain this as we simulate the protocol, we look at Alice's consistent input, or rather we have a subset of this. For this set, we want to make sure that even if we suddenly in this set commit to all coordinates except I, there are still many choices for what xi might be. Okay. At a high level, how is our simulation going to be? So we're going to have an algorithm, an evaluation algorithm that takes this communication protocol as an offline input and then can query the input Z. So suppose we are at the node B again in the protocol. So two things can happen. There are like two types of events in our simulation. One is a communication event. So somehow we're simulating a communication between Alice and Bob. And basically, so someone is speaking in real communication. Both Alice and Bob are speaking. In deterministic communication, one of them is speaking. But the idea is that we somehow want to send safe messages. Alice will send something AV or Bob will send BV. These might be bit vectors that shrink the sets A and B, which are the possible inputs that we're maintaining, as little as possible. Okay. So when we have decided we commit to something that they're communicating, that will make us move to a child W of V in the decision tree. And it's kind of clear now that naively, what we have to update A to is A intersection what is consistent in this child, and similarly for B. Y. So this is like the main thing, that we will find safe messages to send. Based on these messages, we move to a child node. We have to update the consistent sets A and B. And then maybe these sets are no longer so nicely structured, so we have to clean them up somehow to restore properties that we want to hold. For instance, like this property here, that Alice is unconstrained. We're still fairly untechnical. We'll all make all of this precise, but there is a question.
Yeah, I mean, I don't quite understand why we're talking about we will send the messages. Aren't we given a protocol and now we have to extract the tree from it, so we cannot decide anything about the messages?
We totally can, because we're given a protocol, but we haven't committed to what Alice and Bob's inputs are. So we're running the protocol over sets of potential inputs. This is very important. There is no input to Alice and Bob. We have no idea what these inputs are. So we're going to sort of simulate the input and commit on the fly to what Alice and Bob's inputs are. But the point is, what are Alice and Bob's inputs? Well, there is some kind of input Z, and we know that Alice and Bob has some lifting of Z. There are many different liftings of Z. We have no idea what this is, right? That's the whole problem. So we actually have no idea what Alice and Bob's inputs are. Like if you know what Alice and Bob's inputs are, then you know Z, and we don't have the problem, right? The whole point is that we have no idea what this is, therefore we have no idea what Alice and Bob's inputs are. So we're going to simulate the communication protocol over potential sets of inputs. So at the very start, our very first round, we start at the root of the protocol tree. Alice could have anything, Bob could have anything. Suppose that Alice is the first to speak, and suppose she just sends a bit. Okay? Then basically what you want to do, then you measure, okay, two choices. Which one reveals the most about Alice's input and which one really reveals the least? Then we just say, let Alice speak the least informative bit. And then we just move to that subnode W and update these. And then we repeat this. And at some point, obviously, Alice and Bob are starting. Suppose now that Alice is hitting a certain coordinate very, very hard. So she keeps communicating, and you realize with horror at some point that she has actually communicated all bits of X for the first coordinate. Then at that point, we can no longer delay. Because now Bob will probably respond, what actually that value in the vector is, in his vector. And we have no idea, right? How could we figure out at that point? Well, at that point, we're going to say, oops, I guess I actually have to query the first coordinate. Okay, suppose that Alice reveals that x1 is 42. Once she has revealed that, we realize that, okay, Bob is now going to return y42, so we have no idea. So quickly, we issue a query, a decision tree query to ask what is Z1. Turns out that Z1 is 1. Okay. Then we make sure, we say a prayer that B is consistent. There is some subset of inputs where actually y142 is a 1. Did I say that Z1 was 1? I don't remember. It's fine. Okay. So if Z1 is 1, then and Alice revealed that coordinate 1 is 42, then y42 1 has now to be 1 in order for us to be consistent with Z. But we have made sure that B is so, dense with possibilities that in particular, that is one possibility. And in that point, we move to that node, and then we have to shrink B to someone. Now we're committing to that coordinate that Alice, in the continued simulation, we will commit to that Alice had 42 for x1, and in Bob's coordinate, he had y142 true. And then we continue the simulation, but we have now removed coordinate 1 from R. Okay. We still have no idea what Alice and Bob have in the other coordinates, and we're trying to maintain a lot of freedom because the only way we can pin down, like if we ask a lot of information about Z, then it would be easy to simulate, but then our query complexity would go out of the window. The point is, we can only afford to issue what we need to argue now. We're getting a little bit ahead of ourselves, but what we need to argue is that I'm only forced to issue a query when Alice and Bob has already communicated quite a lot. That's sort of the whole name of the game. Am I making some sense? Okay, so this is bringing us to the query events, I guess. Let me remove the simulations here. So the query event is intuitively, we're still doing intuition, but a query event happens in the following scenario. So we have now done some simulation. We are at the node V, and we're looking at the sets, and we realize, for instance, that this condition is false now. It is not the case. We found some coordinate I such that if there is some way to committing to other coordinates so that we have precious little choice for xi. Okay, that makes us nervous, and we realize the only way we can resolve this is we somehow have to commit. We will need to query Zi and figure out what the value is. Okay, so the scenario here that some coordinate I is too constrained. And again, when will it be too constrained? We're getting a little bit ahead of ourselves, but pretty much I'm never going to worry about Bob because Bob has so little information. We're worrying mostly about Alice. There's a huge asymmetry here. So Alice coordinate I is too constrained. What does it mean? That this thing no longer holds. We're going to make it precise in a few minutes. So then we're going to issue a query to Zi, and we're going to get a value back. Note that we have no idea what value we're getting back. We have no control over this. So now we have to fix an xi and a zi such that the indexing function is zi. They say, of course we got this value. This was what Alice and Bob were thinking all along, right? And these sets must be so large so as to allow us to find these possible choices. Am I making sense? Maybe some sense. Okay. And now, obviously, this I will now shrink A and B, and I will remove I from the index set of unqueried indices. Basically, now I have committed to exactly what this is. And so sort of the way to think about it, I now fix all information on Alice's side and Bob's side about this coordinate, so that if there are any queries about this going forward, we're just committed to it pretty much. Okay? And then one final thing is, okay, what do we do when we reach a leaf in the protocol? So we're going to simulate the communication protocol by trying to give as informative messages from Alice and Bob as possible. Like at every node, we say, what's the least informative thing Alice can say? What's the least informative thing Bob can say? And when they still manage to communicate so much that a coordinate is constrained, that's when we issue a query. And the argument is going to have to be that every time we issue a query, they must have communicated quite a lot. That's how we make sure that the number of queries sort of line up with the communication. Okay, suppose we can do this, and again, importantly, it's very important that we have enough flexibility that when we get the query back, that we can line up and shrink Alice and Bob's consistent set so that this is true. Again, we're going to make this more precise later, and also we're going to spend the whole next lecture on this. So we're still developing our intuition. Suppose we reach a leaf in the communication protocol. Well, then actually Alice and Bob have figured out enough information to be sure what the answer is. And then since we have maintained our invariance, basically we're saying, yeah, we have learned enough of Z to be sure that the answer is valid also. This requires an argument, but it's basically Okay. And how are we going to, again, so one final thing, so as I already said, to control the number of decision tree queries, we're somehow going to measure the density of Alice's set A. Okay. We'll define that in a bit. Basically, the intuition is going to be the following, that when we do a communication event, then the density in fact goes up. Okay? When we query, that's when we have to commit to something, then the density goes down. And then via some potential argument, we're going to say that the density is always non-negative. Then you can sort of see that, well, this will be a way to amortize, to say that suppose then the queries can't be out of control, because if we're making a lot of queries and we still have non-negative density, then there must have been a sufficient amount of communication. Okay. So far, what I'm telling you is extremely generic and fluffy. This is sort of a general paradigm for how you build these simulation protocols. There's one twist that we are going to have to deal with, and that is the following, that usually in most communication protocols, you sort of have these notions, and then whenever a coordinate goes bad, you immediately issue a query, and then you continue. Because somehow you have to issue a query, you have to take your Z, you have to commit, you have to clean up, and then you continue. Okay? We are not going to be able to do that, because suppose Alice is in the middle of a long message. Then if we issue a query to the decision tree now, and then only continue the simulation, then the number of rounds here would not match the communication rounds. So what will happen for us is that we realize, oops, Alice is going low on coordinate I1. I have to query that. I make a mental note and do some cleaning up. And I say, oops, Alice has only started speaking. Okay. She continues to speak, coordinate I2 goes bad. I say, okay, we're in trouble. I do some further cleanup to try to deal with that. I make a mental note that I need to query I1 and I2. Please, can she stop speaking? No, she continues. Okay, and I3 goes bad. And I accumulate a lot of coordinates, and I do some cleaning. But the problem is that the standard cleaning that you would do in the Göös-Watson framework that has been developed and then extended to other settings is you would query the decision tree, and that would guide how you clean. Our cleaning somehow will have to be in such a way that we clean now, but we need, for every bit, we need to be able to deal with both the 0 and the 1, and we can only actually issue the queries at the very end when Alice is finally done speaking. Okay, and that's going to be, that's one of the main technical challenges for us compared to Qt. Okay, and because of that challenge, another major challenge is to deal with the fact that, again, in order to model cutting planes, we need this real communication, and this leads to these combinatorial objects that we encountered in our last lectures, these so-called combinatorial triangles. Those also are a rich source of complications. Let's deal with one thing at a time. Let's deal with the round efficiency today, and let's maybe deal with combinatorial triangles some other time. Okay? So that's why I'm only going to do deterministic communication. So our modified theorem that we'll start. So we'll start to prove it today and develop some intuition for it, and then hopefully complete the proof next time. Is going to be something like the following. So suppose there is a standard deterministic protocol solving lift of the search problem S, where again the lift length is as usual. Communication C are rounds. Then we're going to extract a parallel decision tree in depth R with O C over log L queries. Well, we're going to make our life easier by saying Alice and Bob only send bits. Yeah. Okay, let's start setting things up. We need some magic constants, but maybe let me defer. I'll introduce them as we need them, maybe. So we already said that we're going to maintain an Alice set and a Bob set. So again, we're sort of going to fire up the simulation of the communication protocol, although we have no idea what Alice and Bob's inputs actually are. And again, I is the set of non-queried coordinates. And sometimes just to ease our notation, we're going to write for a set, we write A sub I to indicate that A sort of lives on the coordinates in I, just as a helpful piece of notation. Okay, and also for vectors, if I write like X subscript capital J, that means that J is a number of indices, and the vector X somehow lives on these indices, on these coordinates, which will always be non-queried coordinates. So piece of notation is that suppose that I and J, so we're setting up some notation here. Suppose that I and J are sets of indices that are disjoints. Then I'm going to write xi dot xj to be the concatenation. Except it's like a coordinate-aware concatenation. I mean, if the coordinates and I and j are interleaved, then this will sort of this will place the coordinates at the right places. Am I making sense? Okay, not yeah. Good definition by hand waving. One important other thing is to say the projection. So we're going to say suppose that I, the set of coordinates I, live in a larger set of coordinates j. Then I'm going to say that the projection onto I of a vector xj, that is a vector x living over I such that there exists some other vector xj minus I such that xj is the concatenation of xi and xj minus I. This is to say, like, I have x over a large coordinate set, and then I just pick out the coordinates that I like. This is just a complicated way of saying that. And we can also extend this to, if we have a whole set of vectors, then I can project these vectors to a bunch of coordinates and get us another set of vectors. Is this making sense? Because this is basically, this is what will happen anytime we query a coordinate, then we will need to project to the remaining coordinates that are still live. Okay? So we've finally reached the point where we can talk about what are the properties we want Alice's input to satisfy. Okay? So the fact that we're now, what do we want to measure? We want to measure how constrained given in the current simulation, how much flexibility is there for Alice with respect to what the ith coordinate might be? Right? And recall that the intuition is that even if somehow someone decides about all of the other coordinates Alice has, there's still a lot of wiggle room, like what the other coordinate could be. Why is this important? Well, because we have no idea what z variable we might need to match. And so it's important that there's a lot of flexibility for Alice how she could point in Bob's vector, because also for Bob's sides, we're going to maintain like a lot of flexibility of what his bit strings could be. And if we have flexibility on both sides, then hopefully we'll be able to point to both a 1 and a 0. That's kind of the idea. Yeah. So we'll build a bipartite graph. So again, this is Alice's inputs. I'm indicating that the unqueried, non-queried indices are capital I, and little I is one of these indices. So I build a bipartite graph. The left vertex set are just xi. So basically, I mean, what are the possibilities? Well, any value of L. The right vertices indicate what the possibilities are for the other sets. So this lives in L to the I minus I. Where again, this is sort of a, what is this notation? This is a vector where I keep track of what the actual coordinates are. Not only that it has the right dimension, but we're somehow keeping track of which the coordinates are. Okay, and the edges, we have an edge between xi and xi minus I if this is consistent with something in Alice's set. So if, in fact, xi minus I concatenated with xi lives in A. Do we want to see an example of this? Let's do an example. Suppose that we have not queried indices 1, 2, 3. Suppose that the lift length is 3, because that's borderline what we can deal with on a whiteboard. And suppose that currently we're at a node where Alice says she could have, consistent with reaching this node in the protocol, Alice could have any one of these bit strings. Like she could have 1, 1, 1. Sorry, I guess integer strings. She could have 1, 1, 2, 1, 2, 3, 1, 3, 1, 1, 3, 2. All of them with 1 in the first coordinate. With 2 in the first coordinate, she could have these guys. With 3 in the first coordinate, she could have these guys. Okay? So let me build graph 1 AI. So what should I do? I should, on the left, we have all possible values of L, 1, 2, 3. On the right, we have all possible values in coordinates 2 and 3. This is this. And now we're going to have fun, because now I'm going to try to build this graph. Let's see. So this tells me that 1, 1, 1 is in the graph. 1, 1, 2 is in the graph. 1, 2, 3 is in the graph. 1, 3, 1 is in the graph. And 1, 3, 2 is in the graph. We have 2, 1, 1 in the graph. 2, 2, 2. 2, 2, 3. 2, 3, 2. 2, 3, 3. Am I making sense? Then we'll spend some time like, why are we doing this? Well, let's finish the graph and let's talk about it. We have 3, 1, 2. We have 3, 2, 2. We have 3, 2, 3. 3, 3, 1. And 3, 3, 3. Okay, and it's clear I could build also a graph 2 and graph 3, yes? Okay, why am I doing this? What's the point? Well, remember our intuition was that even if I commit to everything else, there should be wiggle room for a certain coordinate. This graph 1 measures the wiggle room for the first coordinate, because the point is, if I commit to any of these guys, I want basically to have many neighbors on this side. Am I making sense? Okay. Firstly, note that there are some nodes that are not terribly interesting. Okay, we know already that this is not something that Alice has in coordinates 2 and 3. We've already ruled them out. Well, we're at the point in the communication where she cannot possibly have these values. So we can sort of think of them as not being interesting for the graph. Okay, but for all others, it could be that, you know, 1, 1 is maybe, I mean, maybe we'll make some queries later, and it turns out that we will have to commit to 1, 1 in order to be able to deal with, you know, find bits for Bob so that we match Z2 and Z3 that are returned by the queries or the decision tree. And we would be worried if basically if we find a guy here that has few neighbors, that's a source of concern. However, if for all vertices here we have like many neighbors, what do we mean many? Well, you know, some almost L. Maybe L to the 1 minus epsilon, something like this. That would be fantastic, right? If we could get square root L, that's maybe good, but you know, I might be getting nervous. We need to do the calculation. Okay. So in order to measure constrainedness, we're going to look at these graphs and we're going to look at the degrees, the right degrees. Okay? Good. So we're ready to do some formal definitions, and then we'll see if we can get to a point where I was planning to get to a point where I could sort of cheat my way to actually presenting the simulation algorithm. I am not sure whether we can get there, but let's see. At least what we're trying to do, we're going to spend the time that remains now. Let's see for how we don't have the energy to talk for too much longer, but we'll talk a little bit longer because we've reached a point, like we really need to understand this. We're going to work heavily with this graph next time. So we need to develop some intuition. In particular, so one interesting measure is the minimum degree for the I graph. That is the minimum non-zero right degree. Again, because if I have a 0 degree, this just means that, well, these are out of the picture. I don't care about them. But for things that are still, you know, potential outcomes, if the min degree is small, here the min degree is 2. Okay? And if the min degree goes too low, then I'm worried. I'm also going to look at the average degree, which is again the average, again non-zero degree. And now we're going to set a parameter. Let's see. Here comes the first magic parameter, but I think I am. Let's define the parameters formally next time. Let's just say that we will consider I to be unconstrained. Like when are we happy with the state of coordinate I? we are happy if the average degree for coordinate I with respect to the current set is L raised to the power of lambda for a lambda that we'll define exactly next time, but it's going to be roughly 1 minus epsilon. It's not the same epsilon, it's some kind of epsilon prime. Okay. So know that what's the best we could hope for? The best we could hope for is lambda, right? We don't, obviously we're not quite going to get that, but we're going to get, so the best we could hope for is L, but we're going to get L to the 1 minus epsilon. That's what we're shooting for. So almost full flexibility. We're going to say that this set is thick. This is a good property. You should think of this as a happy property. This is a property that we want to hold at all times. If for all I, the minimum degree of I is at least L raised to the power of some other magic constant mu, we're going to have mu to be 2/3. So it's significantly lower. It's the worst case. Like on average, we want to have really good degree on the right. But then when we look at the worst case, clearly it's going to be worse, but it's still like it's significantly better than square root f. Okay. This thickness is when we're talking, Alice, when we're simulating the protocol and sending uninformative messages, thickness is something that has to be maintained at all times. Okay. When we lose thickness, then we have to query. Okay? Are the difference making sense? The definitions making sense? No sense? No sense? You have to ask, like, so again, we're only setting, we won't get far to any formal proofs today. We probably won't even state the lemmas today, but this will be the definitions that we will state lemmas about next time. So basically the outline is already, so what are we going to do? We're going to start the communication protocol at the root. We're going to send uninformative messages as long as, and then we're going to move down in the protocol tree. This will update the A set and the B set for Alice and Bob, right? As we move down, these sets shrink and shrink. As long as Alice's set is thick, we're fine. Okay. Whenever we realize in a coordinate that Alice is no longer thick in a coordinate, we need to query. And then now we need to argue two things, that we can, at that point, we need to be able to deal with both 0 and 1. And then we're going to describe how we clean up Alice's and Bob's sets. And this cleanup will then have to restore thickness. Like if little I is a bad coordinate, we'll query that, and then we'll have to argue that now we have restored thickness of I minus little I. And then we continue. This is sort of the name of the game. Okay. We have, is this making questions on this? So like, I mean,
yes, maybe the only thing that I'm asking myself is why on one end we are looking at the average degree, on the other end the minimal degree? Why not define unconstrained?
No, we always want to maintain the thickness.
Yeah, for sure. No,
the fact that we can, okay, good. The reason that we're going to maintain, we're able to maintain thickness is that on average we're going to be much better. So there's going to be an argument like that. It's sort of similar to in all our other, like if there's something bad, then since the overall average behavior is so good, we should be able to like take care of this bad thing and remove it, and then how many bad things can there be? Well, not too many bad things, because then the average situation should have been much worse than this. Note that we have, like, there's a lot of slack between these two. Sure. So that's sort of why we're going to play with both of them. So that's a good question. Yes. Okay. So one observation about average degree. So the number of edges in the graph how many edges do we have in this graph?
Average.
I claim that the number of edges is this. Right? Once we say that I want the I graph, like I just went over all of these and added one edge per guy. That's the number of edges. Right? I mean, for every element here, I just took this one to the left and those one to the right and added an edge. And obviously these are all different, so all the edges have to be different. So the total number of edges is this. How many non-zero elements do I have on the right? So the number of non-zero elements is project on I minus I and see what I have. Right? I project on coordinates, I project away coordinate number 1 and look only at 2 and 3, and I see what is supported. That's exactly the guys here with non-zero degree. Are you with me? Okay, but then the average degree is this. Okay, not rocket science, but this is going to be helpful. Okay. Here's another super important observation. So the minimum degree, and hence also thickness, can only improve under projections. Formally, for any j, for all j that is in I minus little I, I claim that if I look at the min degree of j in the graph where I project out little I, that min degree is at least the min degree for the j graph before projecting out little I. The proof of this, if you think about this, is basically, well, suppose there is an edge between 1, 1, and 1. And suppose I project away the second coordinate. Okay, then clearly all the neighbors of this guy will still be neighbors. I mean, I'm just removing the second coordinate. So I cannot lose any neighbors. However, what can happen is that 1, 1 and 2, 1 and 3, 1 sort of collapse into a single vertex. So I can actually pick up neighbors. Okay, let's actually do a proof by picture of this. Let's see. Let's look at AI minus 2. Okay, so I remove these, I remove these, I remove these. Okay, and now we're going to look at graph 1 of AI minus 2. Okay, so this is in coordinate 3. I now have 1, 2, and 3. And following my previous color coding, I have 1. I have 2. I have 3. Let's look at this graph. What do we get? Okay, so for 1, we're picking up 1, 2, and 3. Right? For 2, we're picking up 1, 2, 3. And for 3, 2, 3, 1. Okay, suddenly I got the complete graph now. So projection, this was already, somewhat decent, but this is amazing. This has like perfect thickness. Okay, proof by picture, this could not possibly be wrong, right? I mean, it had to be true. No, but seriously, I said again, the argument is that if I just remove this coordinate, I save all of my neighbors, but this will merge with this and will merge with this. So the neighbors of this new node will be the union of these neighbors. So the degree, the important thing is that I'm looking on the right degree here. The right degree could not possibly decrease, but we see that it can increase. Okay. This is going to be important for us. We're almost done with shoot. Let's define the final technical notion that we need, and let's talk about it for 5 minutes, and then we'll call it a day, and we'll do all the proofs some other beautiful day. We said that we need to look at the density. So this is the final thing that we need to look at density loss. For non-queried vertices. Okay. So there is an Alice measure and a Bob measure. The Alice measure is alpha. What's the density loss of AI? Okay. The density loss measure basically how far are we from Alice's set currently? What's the best case scenario we could possibly have? Well, the best case scenario would be that Alice had everything, right? Then the set would be of size L to the size of R. That would be amazing. Then we have like everything is consistent with the current state. What we actually have is this. So we somehow want to compare this. And I'm going to do it by taking the log and minus. Okay. Which will, if I work it out, so I will have I times log L minus logarithm of the actual size of A. All logarithm are base 2 as usual. Okay. So for a perfect, at the beginning, what do we have? Well, at the beginning, I has exactly this size, so then we have density loss 0. As the density loss increases, I mean, if we would have density loss I log L, then it's catastrophic, right? So we want to make this small, the same definition for Bob is going to be beta of VI is going to be minus log, best case minus actual. So VI is what we have. What we could hope for is 2 to the L times I. So and this, unless I screw up, is going to be I times L minus log of BI. Okay. And now again, we're still at a very intuitive stage here, but we can now get to a point where we can at least hand wave what's going to happen. One thing we're going to hand wave, we already did. We're going to say we want to maintain thickness. When thickness goes down, we're going to query, and then thanks to the case that the average situation is so much better, we'll be able to restore thickness. And we're going to have to work for it, but it can be done. And density loss is something that's going to be important. And the thing that we saw over here is that somehow projection could be amazing. This is something that we saw. And this is not a coincidence. In fact, so what happens when we project, that obviously like the total number of choices decrease, right? I mean, when we project, obviously the total number of tuples goes down, but also the number of dimensions go down. And in fact, the density increases. Meaning that when we project, the density loss decreases. So projection will help us decrease density loss. Okay, this is maybe the final formal thing that we say today. So formally, we have the following observation. So look at the Alice's density after projecting out coordinate little I. Then the claim is that this is the density loss we had before, pi I minus log L plus the log of the average degree of I in pi I of A. Okay. So when I project out the coordinate little I, how does the density loss change? I have the density loss from before minus log L. And note that the average degree cannot possibly be L, right? It can be close, but will definitely always be less equal. So in general, this negative guy is larger in magnitude than this positive guy. Okay. How do you prove this? I don't know. I don't know. We could do it if you want, but basically, we're just gonna. I mean, here's the definition. So basically, plug this in, move this over to the right, and do the subtraction. Then you'll see you pick up this minus log L, and then you're going to have plus log this minus log this. Okay, but that is log average degree, which is this guy. So really, you just plug in this definition twice and use this thing. There's nothing happening, okay? Do we do this or like, no, we want to finish now? Maybe we want to finish. Okay, good. So where does this leave us? Well, this leaves us at a point where we definitely want to wrap up the lecture. And at the point where I'm also a little bit sure where I left my notes. Oh, over there. Good. So basically, what the algorithm is now going to be the following. So basically, we start out at the top. So what we need to do next time is we start out at the top. We start sending uninformative messages from Alice and Bob. And Bob is basically always going to be uninformative. So don't worry about Bob. Poor Bob. He's like, nobody cares about Bob. So as long as everything is uninformative, we're good. Whenever we lose, whenever the average degree goes down too much, then we query. So sorry, I had this wrong. So already where average degree goes down, we query. Then we have to deal with the fact that in a standard simulation, we would immediately query and restore. We won't be able to do this. We're going to let Alice speak, and we're going to collect bad we're going to collect bad coordinates that she has to query. Every time we have a bad coordinate, we're going to identify a set of possible values for this coordinate for Alice, such that for all coordinates in this set for Alice, Bob could support both a 0 and a 1. And then we continue. This is somehow because we are not able to, we are not allowed to issue the query yet. So we have to identify a hopefully somewhat large set of positions for Alice where we could say, yeah, she had this value. And Bob, in the B set, we are able to consistently answer both 0 and 1 because we don't know what we'll get for the decision tree. Okay? And we're going to keep doing this. Alice continues, as long as Alice speaks, we're going to do this. And as soon as a coordinate goes bad, in that coordinate, we already commit ahead of time that, okay, Alice has one of these values, and Bob is able to support both 0 and 1. Okay? And this is going to be a so-called project step. And then what we're going to do is to, again, just we let Alice speak as uninformatively as possible and move down the decision tree. Okay, once she communication protocol tree. When she finally stops to speak, we issue all the coordinates. We see what values we actually have. Now, by a lot of blood, sweat, and tears, we know that for all of these coordinates, Bob is going to be able to support both a 0 and a 1. Now the decision tree tells us what we need to support. So then, at that point, we fix Alice's coordinates and Bob's bits to be consistent with this. And then we need to do a cleanup step and to restore all the nice properties. And then we keep going. Okay, so next time we're going to have and one important step is that once we, okay, so the final thing, once we move down in the protocol tree to a child node, we lose the nice structure. So then we have to clean up Alice's set. We have to make a pruning step that restores the nice properties. So the key is somehow we need this projection lemma that says that there's a large set of coordinates for Alice where we can support both 0 and 1 for Bob. This is one technical thing that we need to do. This is a projection. We need a pruning step that says that when we go down in the protocol tree and Alice's A set goes bad, we can restore nice properties. And then we need to say, okay, given that we have this, what does the overall algorithm look like and how does things work? That's what we're going to have to do next time. Okay? And again, what are we're going to use average degree, we're going to use thickness, and we're going to measure density loss and play with these graphs. Okay? So that's the plan. But I think it's, high time to call it a day. Any questions?
So just do one list. What's the word after total number of
Choices.
choices?
So what I just meant is like basically when you project the coordinate, when you project here, we project the A, and then we project the I, we project the I, and then we project the I minus little I, then the total cardinality of this set is obviously smaller than the cardinality of this set. So like the size of this guy is larger than the size of this guy. Yeah. Of course, right? But note that when we measure density, we measure with respect to the size of I, and here we measure with the respect to one size smaller. And then we say that the density will go up. And this is like but again, this is like really just the density definition, here it is, average degree, here it is. Just plug the densities in and check that you get a final log thingy, which is actually log of it. Yeah. So there's nothing happening except that somehow this is exactly what we want. Okay, good. Thank you.